Uh, yeah. Hello, everyone. Welcome to this week's seminar. So today it's our great pleasure to have Charles Yuan from Assistant Professor at Computer Science from UW Medicine. So, so basically today, Charles will talk about some compilation work on blocking coding of quantum for quantum computational linear algebra. So, Charles, feel free to take over the stage. Yeah, looking forward to the talk.
Great. Thank you so much, everyone. And I'm really happy to have the opportunity today to share with you the work that we've been doing. So I want to get right into things by saying that, broadly speaking, the topic that I study is programming systems. And what that means is all the things that developers typically use every day: programming languages, compilers, libraries, runtimes, program analyses, all of these sorts of great tools that software engineers use every day on classical computers. Now, what do all of these systems have to do with quantum computers? Well, I tend to view the state of quantum computing as a field, as one where we need to continue to understand and solve problems in a couple of different focus areas that include algorithms, computer architecture, software, and the benchmarks that we can use to evaluate these things. And we want to do our best to bridge the gaps between the communities that study these different topics. Starting with algorithms, right? The state of the field is that what we want to do in the coming years is to run these really great large-scale algorithms for really useful applications like simulation on early fault-tolerant devices. Now, doing this is going to require us to express a lot of complex algorithmic structure and tailor it to hardware costs. Naturally, this calls for better tools like programming languages and compilers. But there's a little bit of a problem in that what most programmers are going to use today to express a quantum computation is very much at the circuit level. So on the slide here, I have an example of a programming primitive that you might find in something like phase estimation in Shor's algorithm. It's essentially a loop, a for loop that executes some operation some number of times, where that number of times is being given by a quantum integer in superposition. And in order to implement something like this operation in a language like Microsoft's Q Sharp, what a developer would have to do is lay out the individual controlled logic gates acting on individual qubits in the system. So this is a paradigm that has served us very well for implementing a lot of textbook algorithms. You can implement Deutsch-Jozsa very well in this. But does it scale to the complex quantum circuits and applications that we find in algorithms papers? Well, frankly, we don't even always find these very specific descriptions of quantum circuits in these papers. We're oftentimes left with only a bunch of English and math and have to piece it all together, right? A lot of these quantum algorithms, the most complex and useful ones, have never actually been explicitly written down as a circuit that we can execute or even analyze. Shifting gears a little bit briefly, we can also talk about the state of computer architecture. And I think the field has concluded at this point that quantum error correcting codes are describing the most natural, though perhaps still evolving, bottlenecks in our understanding of how quantum applications are going to scale in reality. And they really tell us that some small asymptotics that are being promised by the big O notations of these algorithms can actually blow up to be really big constants. This again calls for software tools, really good compilers and optimizers to help us target algorithms to these devices. But what are the authors of these software systems, compilers and optimizers, actually targeting? Well, for a number of years now, the community has been relying on a set of circuit-based benchmarks. Many of them came from this really great paper by Nam et al. In 2018. A lot of the compiler optimization literature is about reducing the couple of hundreds or couple of thousands of gates in these circuits by a factor of 10%, 20%, maybe somewhat more than that. But are they really telling us how we are doing at scale in comparison to the most realistic resource estimates that we have for promising quantum applications like simulation? You can glance at this table here and see that the number of gates that we're really going to need to run on these devices is orders of magnitude more than what our benchmarks are telling us. So while I can't promise to solve all of these problems for us today, I want to argue that at the heart of all of these concerns is the opportunity for us to build new programming systems to bridge the gap between algorithms, architecture, and software. So you can have better tools to express and analyze algorithms, to tailor them to architectural costs, and to just understand how well we are doing. Okay. So in the rest of this talk, I'm going to tell you about some of my recent research on building tools and compilers for certain classes of quantum algorithms. And toward the end of the talk, I want to go a little bit broader and share with you what the overall vision of my research group here at Madison is about. So let's get right into the technical aspects. The class of algorithms that I want to talk about today are these algorithms for computational linear algebra on a quantum computer. So this starts out with, for example, the HHL algorithm for solving systems of linear equations, came out in 2008, been a humongous inspiration since for a lot of other cool algorithms in domains such as physical simulation, regression, differential equations, and much more. And I would argue that linear algebra actually has an even bigger role than just these applications that I showed you. Because a lot of our modern understanding of quantum algorithms as a whole is through a linear algebraic description. HHL obviously is about taking a matrix and inverting it. That's quite literally linear algebra. But even in more surprising places, like quantum simulation, which is all about taking a Hamiltonian A and computing its time evolution operator e to the minus IAT, or in places like database search. For example, this great grand unification paper by Martin et al. In 2021 showed that you can actually take amplitude amplification, phase estimation, all of these algorithmic staples, and represent them also in terms of linear algebra. For example, Grover's algorithm becomes something like a matrix sign function, where you can loosely think of this sign function as distinguishing between cases that you do and do not want to pass your threshold. So what do these algorithms promise us? Well, it's exponential speedup, right? The really awesome thing about the HHL algorithm is that given an n by n matrix A and a vector B, we can solve the system AX equals B for the vector X in time that is exponentially faster than the best known classical algorithms for this task. You can tell that this is the case because the quantum complexity of this algorithm is polylogarithmic in the dimension n of the algorithm, whereas any classical algorithm would be at least polynomial in n. So this polynomial to polylogarithmic, that's an exponential gap. Now, why should quantum computers be so good at linear algebra? Well, it's because they are linear algebra, right? I mean, our understanding mathematically of what a qubit is a vector in a complex vector space. And the operations that we're performing on these qubits, our standard quantum logic gates, are unitary matrices that we're performing matrix vector multiplication on. Okay, so that's at least some intuition for why these algorithms should work like this. But maybe upon seeing this big O notation, something caught your eye, which is that it's a little bit sketchy that a quantum algorithm ought to be able to invert a matrix in time that is less than what it would take to just read all of the entries of that matrix, right? If you've got an n by n matrix with n rows, you're going to need at least O of n time just to look at every row. So how do we possibly do it in time that's polylogarithmic? Well, this is where the trick comes in, right? Some of the caveats and the assumptions of the HHL algorithm. And it's something that the theory community has been spending a decade on since HHL was developed to try to better understand. In 2019, Yuan Tang proved an incredible theorem that showed that quantum algorithms that aggressively assume the ability to load large dense matrices into the quantum computer can actually be dequantized into classical algorithms that also provide speedups. This effectively means that if your quantum algorithm assumes you can get big arbitrary matrices, it's not likely to deliver any speedup at all over classical ones. In that same year, Gillian, Lowe, and some other authors showed the other side of the coin, which is that if you have matrices that are sufficiently structured, perhaps they're sparse, or perhaps they have some repeating pattern, like the circulant matrix on the slide, or there's some algebraic combination of these structured matrices, that it is possible to use an algorithmic framework called the quantum singular value transformation to efficiently encode and perform operations on these matrices. So one thing that I really want to point out here, for anyone who isn't intimately familiar with quantum linear algebra, is the fact that these algorithms represent matrices very differently from any classical linear algebra algorithm. If I have a matrix like this 4 by 4 matrix A on the slide here, well, any classical C programmer can tell you how they would encode and do operations on the matrix. You allocate some array of floating point or complex numbers, you initialize everything, and then you use for loops to iterate over this array to perform things like multiplication. But that's not how a quantum computer will do it, right? The quantum representation of a unitary matrix is actually just the gate. And so in this case, we can actually just say, well, we have two controlled quantum logic gates whose semantics, when combined, will actually multiply to give this matrix. Right? It's a very concise and sparse representation, but it also presents a very different programming model. So what does this programming model actually look like? Well, what does a programmer need to do in order to implement an algorithm like HHL? Because there is no function that is just going to directly invert the matrix, at least not in the general framework here. Instead, what most of these quantum algorithms papers will do is to take that high-level matrix function and approximate it as some polynomial, which consists of, in this case, addition and multiplication operators on a matrix, and use that to actually compute the function. The example on the slide here is an oversimplified illustrative example of how you might compute the inverse function of a matrix A, but it is mathematically reasonable. And what it shows is that quantum linear algebra is really a programming challenge, right? We have to actually implement all of these operators. And eventually, given the input matrix A, we also have to figure out how to encode that into the system, which we're probably going to do by decomposing it into smaller matrices, B and C here, combining them together via arithmetic, until you get all the way down to primitive matrices that are either just unitary logic gates or some black box circuit of logic gates that we assume that we already have. And so this brings me to the fundamental research problems that we set out to solve. The first one is what I would call the abstraction gap. If a developer opens a paper and sees a whole bunch of math that tells them what quantum algorithm they're supposed to implement, how do they take that math and turn it into a circuit that actually encodes that matrix? Well, if you somehow assume that either the paper tells you what the circuit is or that the developer really sits down and figures out the sequence of gates, then they could use an existing quantum programming language, like, say, Qiskit, to just explicitly enumerate all of the gates in that circuit. Okay, so that's something that they could do today. But an alternative that we present in our work is a higher level programming interface where the developer just writes the math, just uses the mathematical operators on these matrices, and has a compiler that produces the circuits from this abstract representation. There's a second problem that now arises, which I call the efficiency gap. Given an initial circuit that represents the matrix that the quantum algorithm is trying to compute, how do we make this circuit use as few qubits and logic gates as possible? Well, this is a problem that's pretty well studied in general. You could take an off-the-shelf quantum circuit optimizer, run it on these circuits. In our experiments, we get somewhere typically around 30% improvement in the number of gates. But what if I told you that you could exploit the high-level structure of the computation here to drastically remove gates and achieve something more like a 95% speed up, right? This isn't possible for generic circuits, of course, but we ought to be able to do a lot better than generic circuits here, right? So that's the promise that I'm going to make you in terms of this research. And I'm going to explain to you next how we do it. So I want to start out with a little bit more technical explanation of what the core concepts in this programming model look like. We're going to start out with some definitions of how a quantum computer will actually store and process vectors and matrices. As we saw earlier, qubits are vectors, quantum states are vectors, okay? But the thing that we actually need to do in practice is to take an explicit list of real valued coefficients and encode them into these states. We'll typically do this via something called amplitude encoding, which just takes these x sub j's and sets them as the normalized amplitudes of our state here. All right. So this is the spec for the state that we want to produce. What is the circuit implementation for how to prepare this state? Well, this is a very deep topic that in the literature you'll typically see under the term quantum state preparation. You can search for it on Google Scholar and get about 3 million results, which I think is pretty accurate. It's a very hard problem in general, and a lot of people have focused on how to efficiently do this for classes of states that they really care about. The good news is that for the purposes of this talk, what we're going to do is going to work with any existing method for state preparation. So for now, we're going to set this question aside and assume that we're going to have one of these existing techniques to prepare the vectors. Okay, then we are going to need the matrices, right? And as we said, the way that the quantum computer gives us these matrices is via the semantics of the logic gates. Those are our unitary operators. So it would be really nice to take all of the matrices that we care about and to just come up with a way of shoving them into the unitary logic gates. There's a little bit of bad news on that front, which is that a lot of the matrices that we care about are not actually unitary. Perhaps your data input is not unitary. That's not a very interesting case. But a more interesting case is when you want to perform arithmetic on matrices that might be unitary to begin with, but aren't unitary when you add them. In general, the sum of unitary A plus B is not unitary. So that's kind of a problem. In general, it might not be possible or efficient to get a unitary representation of whatever matrix expression you want to compute. The good news is, once again, that the theory community has largely figured this out for us through a concept called block encoding. A block encoding of a matrix A, which is a real matrix of dimension n by n, is just a bigger unitary operator. Here I denoted B of A, and it has A shoved into the upper left corner, where all of the blocks apart from the upper left corner can be arbitrary as long as the overall matrix is unitary. Now, this is possible for a lot of different matrices A. It happens to be the case that if A's spectral norm is too large, then you can't do this. And the solution is to just divide it out by this factor alpha, which is called the subnormalization. It's at least as big as the spectral norm of A, and it just normalizes things to make sure that this encoding can always exist. All right, so again, intuitively what we're doing is we're taking a possibly non-unitary matrix and shoving it into a unitary that is representable by a quantum circuit. Now, why do we want to do this? Because it gives us the opportunity to perform this critical matrix vector product operation. If I take a block encoding of A and I apply it to a vector x encoded in amplitudes, along with some ancillary qubits, then the output here is going to include this ket AX. Ket AX is the encoding of the matrix vector product AX. Now, there's also some garbage here. There's that plus bottom state. That bottom is what I use as notation for an error state, where the ancilla qubits are not all zero. Okay, so that's just this probability that the algorithm screws up, and if so, we have to start everything over again. Another way to say that is that what we'll want to do is to post-select for the cases where the ancilla qubits are all zero, and we do get this ket AX that we want. The probability that this post-selection succeeds is proportional to the amplitude, something about the amplitude here, which if you're using oblivious amplitude amplification and other appropriate techniques, you can show can be done exactly in time O of alpha. So the runtime of a program that is trying to encode a matrix A and then use that to perform operations like matrix vector multiplication is going to take time O of alpha. right? So the subnormalization term here, it goes away in the final output. You can see that we just get ket AX, but it does show up in the runtime of the program. That's very important to remember. Okay, so why are block encodings so powerful and useful as a programming paradigm? Well, it's because theorists have figured out how to perform arithmetic, useful arithmetic, even on non-unitary operations like addition on all of these matrices. In our actual paper, we give you the semantics of all of these operators in our language. They're just these neat circuit gadgets. You can see that some of them are kind of vertical parallelism, horizontal parallelism, or these kinds of select and prepare circuits that you may have seen before in LCU-based simulation. Anyways, you can do all of these things, and then it gives you the core of this language that enables you to just write down the arithmetic operators and then deduce what the circuit has to be. Instead of going through the logic of all of those semantics, I want to show you a specific example of a program. So here's some code on the screen here, which you can roughly think of as describing something like a simulation application, where you might have, say, a system of two particles that might interact either positively or negatively, which I call A and B here. And then we're trying to simulate an overall system that is combining some proportion of the positive and negative interactions. We want to ultimately produce a block encoding of the matrix H here. Here is the circuit that our programming system, Cobble, will actually compile for this program. Again, it does this automatically. The programmer types the top thing and the bottom thing comes out. So with these circuits now, the relevant question starts to become, how much does the circuit cost to run at runtime? So there are two main factors that determine this. The first one is how many logic gates are actually in the circuit. And we can count this. We can look at the semantics of every operator and we can define some sort of function that tells us, for example, that a number of gates needed to represent a linear combination of two matrices is going to be at least a number of gates for the first one and a number of gates for a second one, and then some additional bookkeeping number of gates. Now, that O of 1 term turns out to be pretty dependent on implementation details, like exactly which rotation gates and which controls you're going to do. It's a little bit annoying to do all of that. So one thing we tend to do is to simplify it by asking instead for the number of queries to the relevant basic matrices in this expression, which here are just x's and y's. Right, so we're no longer counting exactly how many RY gates, we're counting how many instances of x and y are showing up in the circuit. Okay, so this is just a little bit simpler. It gets rid of that O of 1 term. The other part of the equation is, like I said, the fact that the subnormalization causes you to need to repeat the process over and over again. So we want to compute this subnormalization explicitly. This is also something that we can do by kind of synthesizing a lot of results from the theory literature, including one that tells us here that the subnormalization of a linear combination of M1 and M2 is the linear combination of the subnormalizations of those two matrices, with the little caveat that the scaling factors lambda have to have their values as absolute values when you're computing the alpha. Right, keep that in mind, that absolute value means that there's no sign cancellation. We'll put all these together and we'll claim that the total cost of this quantum computation is the number of queries to the relevant matrices multiplied by the number of repetitions until the post-selection will succeed on expectation, which is, of course, the subnormalization. That product is what we want to eventually reduce. It's our overall cost metric. For a given program, like the one that I showed you before, we can explicitly and automatically compute this cost just by going through the program, recursively computing what the subnormalization is supposed to be. In this case, you can see that we go through all of the equations and we deduce that this program will take 2.6 iterations on expectation before it successfully produces the matrix H. So the next part then is, well, how do we reduce this cost, right? And there are a lot of different things that you can do. One of them is very simple. I call it sum fusion. It simply exploits the idea that, well, that h right there is clearly not simplified, right? It's got this xx and yy component that should just cancel out. We should just rewrite it as this simpler term down there. And indeed, this is a really great strategy because it actually takes our circuit and makes it smaller. Okay, right? So this is the new circuit. It still block encodes the same matrix H, does so in vastly fewer gates. And more importantly, what we have done here is that we have explicitly canceled out the minus sign. Right? I said earlier that subnormalization doesn't cancel signs for you. So you have to do it yourself at the level of the program. When you do this, the overall cost of the program lowers, both in terms of the number of matrices that you're invoking and the subnormalization. You get, in this case, a pretty reasonable speedup. I said just now, you have to do it yourself. In reality, what we're doing is we're building a programming language that automates that for the developer. Subnormalization doesn't handle it mathematically, so that's why we do it at the compiler and language level. Now, let's try to see how far we can push this idea. Okay, is sum fusion all we can do? Let's go back to this example set of expressions from earlier. This is a set of expressions that we get from regression-inspired applications. It's not particularly important what is going on here in the math, except saying that, well, we want to encode this matrix L, and the circuit on the bottom is the most direct circuit that we can get for this. How do we make this circuit smaller? We could apply the same sum fusion idea, essentially just collecting all like terms, canceling out signs, and we get a more concise mathematical notation. So that's really great. Is this going to result in a smaller circuit? Well, before I give you the answer to that question, I want to give you a little bit of a pop quiz, and it has to do now not with quantum, but with classical linear algebra. Suppose I have matrices A and B, and I want to compute A plus B times A plus B. What is the least number of matrix additions I need to perform to do this? If you take a moment to think about that, you should hopefully conclude that the answer is just 1. Right? We can add A plus B once. That gives us a value that's just a cached value that we can reuse as many times as we want, so we can just square that value. 1 addition, 1 multiplication, we can compute this result. Here's a related problem. If I want to take a matrix A and take its 128th power, how many multiplications do I need to perform? If you think about it for a few seconds, you might realize that you could do this by multiplication or exponentiation by squaring. Okay, so you take a squared, a to the 4th, etc. After 7 multiplications, you can get to a to the 128. Again, all of this is sub-expression reuse at its finest. But does this still work in the quantum setting? Well, here is an expression that arguably uses a lot of sub-expressions a lot, right? And the circuit on the bottom is actually the circuit that we get for it. You'll notice it is not anywhere near as short as the mathematical notation. Right? That's the alarming fact, which is that sub-expression reuse does not in general work for quantum linear algebra. The reason is because we don't actually have an explicit worked out cached form of the expression A minus B. We have circuits for A and circuits for B and circuits of A minus B, and every time that appears in the program, every time that's supposed to be multiplied by itself, we have to actually insert a copy of that circuit. All right? So the big difference between quantum and classical linear algebra is that you can't just use a program-independent method like sub-expression reuse to automatically make your computation a lot faster. What you're going to have to do is exploit additional structure in this program. Most notably, the fact that we're not just performing any additions and multiplications, we're trying to evaluate a specific polynomial with a fixed base. This turns out to be something that we can do. First, we will do some symbolic magic to accumulate the coefficients here so that we're explicitly recognizing the fact that there is one base and we want to compute this polynomial of it with these coefficients. And then what our system will do is invoke the quantum singular value transformation I mentioned earlier. Now, the QSVT is an incredibly deep topic that I don't have another hour to give a lecture on. But suffice it to say that it's something that enables us to derive efficient circuits for polynomials of matrices, where both these matrices and polynomials satisfy certain conditions. And as part of our research, what we'll have to do is, first of all, get this list of coefficients so that it can be a suitable input for the QSBT. And then we can actually check these properties on polynomials about their signs and about their parity, check properties of the underlying matrix like its hermiticity, invoke off-the-shelf solvers so that we can compute the correct rotation angles, and then ultimately generate a circuit. The upshot of all of this is that what Cobble does for the QSBT is enable it to be used as an automated compiler backend for quantum linear algebra operations for the first time. Again, the details of this are in our full preprint. The upshot is that by doing this, we are once again reducing both components of the cost. We're making it so that we call the functions fewer times, and we're reducing the subnormalization, and we can get pretty substantial speedups by doing this. I want to quickly zoom through some of the boring technical details in the actual paper. One of the things that we provide is an explicit mathematical cost model for everything that is going on in this language. So for every single constructor, addition, multiplication, whatever it is, we give you the ability to analytically compute how long the program will take to run, how many ancilla qubits it's going to use. There's a surprising amount of math involved here that comes from the fact that the subnormalization of a matrix polynomial is going to be dependent on one of its polynomial norms, depending on the method that you use. For example, in the naive method that we described earlier, where you evaluate a polynomial simply by adding and multiplying a whole bunch of monomials together, then the subnormalization is equal to the L1 norm of the polynomial. On the other hand, if you use the QSBT, the subnormalization is equal to the L infinity norm of the polynomial. What's the difference? Well, the L infinity norm, you can kind of think about it as allowing sign cancellation to help you out a lot. It's no greater than the L1 norm, and as we saw just earlier, can be substantially less. Based on that cost model, we can build a set of systematic optimizations to reduce the costs. I've already described to you what sum and polynomial fusion do at a high level. Here's what they literally look like as equations. You can see that what sum fusion is trying to do is it's taking these nested sums of matrices and it's accumulating just the coefficients together so you only get one explicit addition of matrices. This looks, I think, pretty simple on the slide. The reality is that the actual compiler is going to require a whole lot more rewrite rules just to facilitate everything from, to be collected together. Okay. And a lot of what we do in this paper is to really formalize the language, the semantics, the cost model, and the optimizations. So let's get to the evaluation then. How well does this thing actually work in practice? Specifically, our first research question is how good is our system Cobble at reducing the costs of matrix expressions? So to evaluate this, one of the things we actually had to do was build a database of benchmark programs for matrix expressions relevant to quantum applications. This isn't something that existed previously because we didn't have any language to write them in. So what we did is we took some of our examples from earlier and also looked through the literature about simulation, regression, image analysis, kind of interesting applications, not all of which are going to be realizable in the near term, of course, but we think are kind of informative of the kinds of expressions that you might actually need to write someday. And we computed the costs of these expressions in our system before and after optimization to show that, at least for these applications, you can get some pretty reasonable speedups. I want to briefly mention these costs here are actually independent of the dimension of the matrix, right? Because as I mentioned earlier, the number of queries to the matrix is what we're counting at this level. All right, so that's about kind of like basic matrix expressions. Our next research question is about how good this Cobble system is at performing resource estimation of kind of known and well-studied quantum algorithms. So what we did here is we looked at a lot of the algorithms from the literature to do things like matrix inversion For example, this optimal polynomial approximation of A inverse from this great paper from 2025, as well as some other kind of recognizable papers about Hamiltonian simulation, as well as the Martin et al. Paper that shows how you can use QSVT to generalize amplitude amplification and phase estimation. The thing with these algorithms is that we're not trying to beat them, right? These algorithms have already been written with the QSVT in mind. It's just that they've never actually been explicitly written out as a circuit with actual costs. And what we're doing here is we're comparing different methods of actually implementing these polynomials. First, via the naive method called LCU, a variant of that, which is Horner's method for polynomial evaluation, which you may be familiar with, and finally the QSVT. What we're showing is that ultimately, yes, the claims of these theoretical papers do hold up. QSVT is an excellent choice, and our system automatically derives some of the first executable circuit implementations of these algorithms. You might not be satisfied with all the claims that I made so far because they're still using our rough cost metric. What about the actual number of gates? Well, we counted those as well. Okay, and our third research question is about how well Cobble performs relative to simply taking those naive circuits and passing them through an off-the-shelf general quantum circuit optimizer. So what this graph shows is that generally our system does very well. I mean, part of that is because the existing circuit optimizers have a much harder job to solve. We're giving them this giant circuit that they don't know the structure of, and they have to do their best to cancel out the Hadamard gates and whatnot. Cobble is able to tie or outperform all of the existing circuit optimizers that we tested against. And we also found that really the improvement that Cobble makes at the high level is orthogonal to the improvement that these circuit optimizers make at the low level. For example, we showed that by running Cobble first and then running an existing circuit optimizer, you're really getting the best of both worlds. There are a number of kind of low-level technical next directions that I like to explore here, like actually generating better circuits so that the circuit optimizers don't do that much more of the job for us, trying to exploit more algorithmic structure and maybe apply more formal methods to the problem so that we can further automate some of the things that we haven't automated. Instead of dwelling on that, I want to share with you a little bit about where I want to go with this project. Because I've presented a language of arithmetic operators over matrices, that may remind you of this classical linear algebra library, Eigen, which is this template-based library in C++ that I think a lot of people use and get a lot of great mileage out of. There's still an open question as to what about more generally the ability to just manipulate arrays and construct matrices and define operators that are outside this base set of arithmetic? What would a quantum version of a NumPy-like programming interface look like? And a related question is, well, we've seen that quantum information by itself provides you with very compact representations of vectors and matrices, and this basic operation of matrix vector multiplication. That's kind of like a basic linear algebra subprogram, as in the classical BLAST library. But what about more complex linear algebra? Spectral decompositions, other kinds of interesting transformations. What would a quantum version of LAPACK look like? I think we're only beginning to understand these questions, and I think we're probably even further from understanding how we can make these things work efficiently on constrained hardware, the way that classical programming systems like TVM or JAX have enabled us to do for GPUs and TPUs. So again, not very well fleshed out, but I think that there are a lot of interesting questions here. And if you're interested in these questions, I'd encourage you to check out our full preprint and, get in touch. Now, I mentioned that what I wanted to end the talk on is a broader note about where my research group is going beyond just this project on quantum linear algebra. And one question that I really think about a lot of the time is how we can take quantum algorithms very broadly and make them work efficiently for real applications on emerging hardware. For our whole community, I think it's not a secret at this point that our hardware devices are going to be very constrained in resources. Constant factors are going to determine whether the asymptotic promised advantage of an algorithm is actually practically realizable. I think we need to continue reducing these factors, and this is going to involve a lot of cross-stack work. Software people, algorithms people have to engage with the architecture community so that we can all build better compilers together. Some of my research that I haven't gotten the chance to talk about today is aimed at studying this quantum compiler infrastructure of the future. I think a big thing we need to do is to take the new insights that are governed by the costs of this new computational model, not just qubits and logic gates, but also things like subnormalization, uncomputation, other kinds of things that we have to do in quantum programs, and develop a system that will automate and integrate techniques to improve these costs that today are pretty scattered in the literature and mostly done by researchers by hand. There's also a very high-level question of whether it will ever be possible for people to program a quantum computer without having a PhD in quantum physics. Is it possible for a developer to be able to use quantum advantage without explicitly writing down individual logic gates acting on individual qubits every single second of their day? The thing is that we've done this for classical programming. Right? We've developed high-level programming frameworks, not just for sequential C programs, but also things like OpenMP that gives you access to these really awesome parallel primitives. We've done this for probabilistic programming as well. Now, it would be really great if we could also come up with some sort of pragma that just tells you make this for loop quantum and magically get some speed up from it. Now, by this point, I think it's pretty clear why we can't just do that, but we still don't want to be programming with explicit logic gates forever. And I want to know how close we can get to truly high-level abstractions. I think this question is probably best answered through a twofold approach. The first is to continue investigating questions of how we can or cannot effectively use fundamental abstractions from classical programming, things like control flow and memory and data structures, and asking, do those things map very well to the quantum world? I have a number of papers on that. And the other direction is to continue engaging with the algorithms community to study the deep abstractions that target the mathematical heart of these algorithms. That's what a lot of this work on linear algebra, block encodings is supposed to tackle. So overall, I would say we've got a lot of work to do to try to get algorithms and architecture folks on the same page. There's so much, in this iceberg of topics of how we're eventually going to program these devices that I was not able to get to today. But I'm really excited about all of them, and I think that this is a great time for us to work together to find solutions to these problems. So if you have any thoughts, please feel free to get in touch. And with that, thanks for listening.
Thank you very much for the great talk. Any questions from the audience? So I saw there's one question from the chat. I think maybe you can, I think the question is running the Cobble first before the other optimizer or after or either?
Yes, I think, yeah, the commenter has said something here. Right, what we are suggesting is that you have a high-level program, right? It's just mathematically representing what matrices you want to compute. You rewrite that math at the high level using Cobble in order to get the best circuit you can. And then if you want, you can run an existing circuit optimizer, and then it can get some continued improvements.
Cool. Thank you. Feel free to unmute yourself and yeah, ask questions.
Yeah, so what is your output? What can Cobble output? How flexible is it? Are you gonna give me a Qiskit circuit or ZX
It's a
graph?
chasm file. It's a chasm file. It's a
Look
list
at
of
it.
gates. We can compile to Clifford T. We typically compile to something like the NOM gate set, so Clifford plus RZ gates.
Cool. Thank you.
two questions I'll ask that are not exactly related, but really great talk, Charles. Thank you. First question is, you hinted at using these other compilers to get kind of maybe benefit of lower level. Well, actually, I'll rephrase my question. Oftentimes, these other compilers target different things that they're optimizing, either like number of 2-qubit gates or
Right.
magic states or whatnot. How much of
Mhm.
that does Cobble know about? Would you want Cobble to know about? Like, how do you think about
Right.
that
I
line?
see. Yeah, yeah. Your first question, how much of that does Cobble know about? None of it. And that's I think what the beauty of this is, right? I mean, LLVM is divided into a front end and a back end. The front end knows almost nothing about the back end. And that is the kind of spiritual intention of what we're going for. How much should Cobble go for it? That's a very deep question, right? I think it's a little bit unclear what aspects of, let's say, architecturally or error correcting code relevant characteristics developers would benefit from knowing at the moment that they sit down to implement these programs. I think it's going to be true for a while now that our devices will be so limited that we can't afford for developers to not think about that. But we still need to work towards developing systems that aren't just kinds of shoving all of the information into the programs that every programmer is trying to write. We have to come up with some principal design here, and I don't yet know what it is. I'm hoping that it will emerge.
And second question, I think was a little implicit in your closing, but kind of tying back to where you opened, do you foresee ways in which Cobble helps answer questions about, quantum advantage, quantum utility, at least in this linear algebra space, or do you think it's
Yeah.
kind of more of a reflection of
Yeah.
other results?
Right, that's a great question. So I think that there's a high level and a low level way in which I want Cobble to be able to help the algorithms community understand claims of advantage. I'll start with the low level one. We provide concrete resource estimates, right? I mean, many of these algorithms have only ever been described in terms of big O. And there's so much work going on these days about just trying to write these really long resource estimation papers to actually tell us how many qubits we're going to need. And I think the more tools that we have to cover a bigger space of algorithms that gives us that, the closer we will get to understanding, okay, with this device in 2035, can we expect to run this algorithm or not? So that's a low level answer. Now, the high level answer, it gets at a little bit of what I was telling you on this slide, which is that the theory community has spent a lot of time telling us, hey, the general case is impossible, right? Dense arbitrary matrices, you can't do it. Now, here is a collection of small things that we points in the space that can be done efficiently. What a programming system allows us to do is to build bridges between these points, right? Knowing, okay, we can do these matrices, and we also have a system that enables us to compose them together into very rich things, polynomials, or using those polynomials to approximate arbitrary and interesting functions, and then studying, okay, how good are these approximations? How big of a circuit is it going to look like? What are the trade-offs involved? I think we're early in the understanding of that, but I hope that this is what programming systems can, again, bring to the table to bridge together the algorithms world and the circuits world.
Great. Thank you.
Cool. Are there any other questions from the audience? Yeah, maybe I have one question. I think you mentioned it a little bit in the talk. So have you tested the compilation in any hardware, or like have you done any like benchmarking on this compared to other like
So
compiler stuff?
we produce chasm circuits, right? And these chasm circuits are things that you can then feed through whatever transpiler you would like and benchmark it on hardware.
I
Now,
see.
the caveat is some of these circuits are still fairly large, right? And I showed you
Yeah.
that our system produces a range of different sizes. Like for trivially small toy examples of matrices, I think these are things that would be really meaningful to try to benchmark on current devices. For larger things that are approximating like, state-of-the-art simulations that we really believe are going to give asymptotic advantage over classical algorithms, we're probably a little bit farther off. But, and I see that there's a question in the chat here as to what, are these examples actually available? I would say spiritually, yes, we have a GitHub repository. In practice, it still requires a whole lot more documentation. We're trying to get this paper through review and all that and think about what the best way is of actually packaging this up for release. But if you're interested, the repository is up. You can actually run this. It's just a Python package. You can get these circuits for yourself.
I am very interested. Could you copy the repository there in the chat?
I
Just
don't, my screen is a little bit crowded right now. If you go to if you just Google my name, go to my website, go to the preprint, go to my GitHub, it is right there. And if you'd like to email me afterward, I'm happy to send it to you that way
no,
as
no,
well.
I'll Google you. That's fair enough. Thank you very much.
Great. Are there any more questions from the audience?
Hi, my name is Shiplu, so I'm a postdoc at Iowa State. So I have some questions, mostly regarding quantum linear algebra and Hamiltonian simulation. Um, so Professor Yuan, I'm just wondering like whether you have further plan. So let's say a Hamiltonian expressed in quantum many-body operator forms in terms of
Yeah.
like creation and annihilation operator. And then if someone
Sure.
decides that some sort of Hamiltonian encoding they want to do, whether it is Jordan-Wigner or other encoding,
Mhm, mhm.
but given in the operator form, do you have any plan and deciding like what sort of Hamiltonian encoding they want to do? Do you have a plan to translate from that form to a circuit? Um, for
That's a very interesting question. I don't have a straightforward answer for you because we're still at the beginning stages of thinking about how specific applications like simulation first translate into linear algebra and then into circuits. Now, you could also say simulation is enough of a specialized subcase of linear algebra that if you already understand that algorithm very well, you could take encodings from Open Fermion or Qualtran or any of these other sorts of projects that specialize it for there. But my short answer is it's something that's on our radar. We don't have a specific way of handling these things yet. If that's something that you think would be really cool to implement in the system, I'd be happy to chat more about that.
I have another questions regarding again Hamiltonian simulations. For example, there are many different techniques to reduce the number of measurements. One of them is unitary partitioning. So you have a
Right?
Hamiltonian bunch of terms, and you just a priori before even implementing, you just partition them into different classes. Within in each class, the operators commute, right?
Yeah,
And then you form an unitary in such a way that all of these terms you can measure simultaneously. But doing these constructions case by
yeah,
case basis, given in Hamiltonian, it's a quite a bit hard work.
yeah,
And and I'm just wondering, like, whether you have this plan of this sort of implementations
yeah.
and
Mm.
finding like the optimal unitaries, which helps to reduce the measurements of the number of terms in
Well,
Hamilton.
that's a really interesting idea. And there are so many techniques out there that I wish that I could say I had a plan specifically for how to integrate all of them. But thank you for bringing that one to my attention. And I'm happy to follow up with you more to see if this is something that we can really manage to prioritize in the near term.
Okay. Yeah. Thank you. Probably I will send you an email. Uh,
Great. Yeah.
Great. Let's thank our speaker again for the great talk. And yeah, thank you so much for giving us this nice ideas like presentation. So we will have another Quantum Wednesday seminar next week. So looking forward to see you all in next week. Yeah, thank you again for the speaker for the nice talk.
Thanks, Charles.
Bye, everyone.
Yeah. Thanks for having me. Bye.
Thank you.